Welcome back to G Fun Facts Online. Today, we're diving deep into a world that's usually the stuff of science fiction, but is rapidly becoming science fact: the world of intelligent robots. We're not just talking about simple factory arms doing repetitive tasks. We're talking about robots that can operate in our complex, ever-changing world, assisting in our homes, or even revolutionizing how things are made and delivered. To do this, robots need to be pretty smart. They need to master something called Robotic Task and Motion Planning, or TAMP for short. Think of it like this. TAMP is how a robot decides what to do. That's the task planning part. And then, how to actually do it, moving its body and grippers precisely. That's the motion planning part. And here's the exciting bit. Artificial intelligence is completely transforming this field. The big challenge has always been connecting the robot's brain for high-level thinking, like figuring out the steps to make a cup of coffee, with the nitty-gritty of actually moving its arm to pick up the mug without knocking everything over. In the past, these two things were often tackled separately. You might get a plan that made logical sense but was physically impossible for the robot, or a movement that was smooth but didn't achieve the actual goal. But now, AI is helping create a much more unified and intelligent approach. So what's in this AI toolkit that's giving our robots such a boost? Let's take a look. First up, we have the classics, classical planning and search algorithms. Think of Dijkstra's or A** search. These are like the original GPS systems for robots, finding the best path in well-defined situations, often used to map out the sequence of tasks. Then there's sampling-based motion planning. Algorithms like RRT and probabilistic roadmaps are superstars when it comes to navigating really complex, cluttered spaces. Imagine trying to thread a needle in a haystack while blindfolded. These algorithms help robots explore and find collision-free paths in high-dimensional spaces, which is just a fancy way of saying spaces with many possible ways to move. For really tricky situations, especially those involving contact, like a robot carefully placing an object or walking on uneven ground, we turn to optimization-based TAMP. This approach treats the whole problem as one giant optimization puzzle. The goal is to find the best way to achieve a task while respecting all the rules, logical rules for the task, and physical rules for movement, like how the robot's joints can move or how it interacts with objects. Now let's talk machine learning, because this is where things get incredibly dynamic. Deep learning, especially using things like convolutional neural networks, or CNNs, is revolutionizing how robots see and understand the world. It allows them to process data from cameras and other sensors to recognize objects, figure out their position, and understand the scene around them. It's like giving robots superpowered eyes and a brain to interpret what they see. Then there's reinforcement learning, or RL. This is fascinating because it's how robots learn through trial and error, much like how a baby learns to walk. They try an action, see what happens, and get a reward or penalty. Deep reinforcement learning combines this with those powerful deep neural networks, and it's showing amazing promise for teaching robots complex manipulation skills directly from what their sensors pick up, even when the rewards for doing something right are few and far between. And what if you could just show a robot what to do? That's learning from demonstration, or LFD. Robots can learn by watching humans perform a task. This can massively speed up the learning process, especially for complex skills that are a nightmare to program manually, or would take forever to learn through pure trial and error. And here's a really hot area right now: large language models, or LLMs. Yes, the same kind of AI that powers advanced chatbots. LLMs are becoming incredibly useful in robotics. They can translate our spoken commands into a sequence of actions for the robot, help generate symbolic plans, and even suggest the precise parameters for those actions. Their common-sense reasoning is a huge help in bridging the gap between what a human wants and what the robot needs to do. Some systems even use LLMs to create initial plans, which are then checked and refined by more traditional planners. Finally, there is Neuro-Symbolic AI. This is like creating a hybrid thinker. combining the pattern recognition strengths of neural networks, which learn from data, with the logical reasoning of symbolic AI, which uses explicit knowledge and rules. For robots, this means they can learn from what they sense, but also make sure their actions are consistent with safety rules and predefined knowledge. Imagine a robot that not only sees a cup, but also understands, through learned symbols, that a cup is something you can pick up and that it might contain liquid. Despite all these incredible advancements, getting robots to perform complex manipulation tasks reliably in the real world is still a major challenge. The real world is messy and unpredictable. Robots need to deal with incomplete information, noisy sensors, and things changing unexpectedly. Planning under uncertainty is a big research area. Then there's long-horizon task planning. Many tasks we find simple, like tidying a room, involve a long sequence of actions. Generating optimal plans for these long sequences is computationally very hard, especially when every step involves both a task decision and a motion plan. Sample efficiency in learning is another hurdle. Reinforcement learning is powerful, but it often needs a colossal amount of experience or data to learn effectively. Collecting this on a real robot can be slow, expensive, or even unsafe. That leads us to the sim-to-real transfer problem. Training robots in simulation is often faster and safer. But a policy learned in a perfect simulation often doesn't work so well in the real world because of the sim-to-real gap. Tiny differences between the simulation and reality. Researchers are working on clever ways to bridge this gap, like varying simulation parameters to make the robot's learned skills more robust. Robots also need a deeper semantic understanding and knowledge representation. It's not enough for a robot to see an object. It needs to understand its meaning, its properties, what it's for, and how it relates to other objects. Think about a semantic map. It's not just a geometric map of a room, but one enriched with information like this is a table, that is a chair. Chairs are for sitting. As robots get more autonomous, explainability and trust, or XAI, become crucial. We need to understand why a robot made a particular decision. If a robot does something unexpected, we need to be able to interpret its actions to debug it, and, more importantly, to trust it. For tasks that are too big for one robot, we have multi-robot systems. Coordinating a team of robots introduces new layers of complexity. How do you assign tasks? How do they share a workspace without crashing into each other? And, of course, there's human-robot collaboration. The future isn't just about robots working autonomously. It's about robots working with us. This requires robots that can understand human actions, intentions, and even preferences in real time, all while ensuring safety. So what does the future landscape look like? It's incredibly exciting. We're moving towards more capable and adaptable robots thanks to these AI breakthroughs. We're seeing a trend towards hybrid systems, which combine the best of different AI approaches, maybe learning-based methods for seeing and grabbing, with symbolic planners for high-level reasoning. End-to-end learning is another promising direction. Training systems that go directly from raw sensor input, like a camera image, straight to robot actions, potentially cutting out a lot of complex intermediate steps. Imagine robots capable of lifelong learning, continuously adapting and improving from their experiences in the real world, just like we do. We're also pushing for increased dexterity and adaptability, developing robotic hands and manipulation skills that get closer and closer to human-level dexterity. LLM-driven interaction and planning will likely make interacting with robots much more natural and intuitive, and their planning capabilities even more sophisticated. Researchers are even exploring how LLMs can help generate reward functions for reinforcement learning or translate complex instructions into formal plans. And to make all this happen faster, we're leveraging powerful hardware like GPUs for faster planning, allowing robots to evaluate thousands of potential solutions in parallel. The journey to truly autonomous, versatile robots that can handle complex real-world manipulation is definitely ongoing. But with the rapid advancements in AI, from deep reinforcement learning and large language models to neuro-symbolic reasoning and advanced perception, this vision is closer to reality than ever before. As these technologies mature and we overcome the challenges, expect to see robots playing an even more integral and helpful role in all aspects of our lives. That's all for today on Fun Facts Online. Thanks for tuning in, and we'll catch you next time with more fascinating insights from the world of science and technology.